Welcome to this explainer. Okay, let's just dive straight into this, because today we are tackling what is arguably one of the most demanding, absolutely high-stakes areas of your entire computer science syllabus. I want you to think of answering these high-mark pseudocode questions like an Olympic weightlifter stepping up to the bar. You don't just need endurance for this, you need explosive power, you need perfect technique, and you need absolute dialed-in focus in these short, intense bursts. Whether you're currently studying Cambridge syllabus code 0417, 0478, 0983, 0984, 2210, or you're specifically tackling the rigorous AS&A level 9618, documenting algorithms and writing pseudocode is literally where the real marks are won or lost. It's the ultimate battleground. Most students, and I mean a huge percentage, lose easy, foundational marks on these exact questions. But after going through this explainer together, you absolutely will not be one of them. We're going to build up your explosive exam power today so you can walk in there and confidently lift those top-tier grades.
So let's start with a really important question, and this brilliantly illustrates the core problem we're facing. Why do you lose easy marks on documenting algorithms in pseudocode? It generally happens because of two very common, very dangerous traps. To explain them, I want to introduce you to two types of students. You might even recognize yourself in one of them. On one side, we have Alex. Now, Alex works incredibly hard. Alex stays up late and memorizes every single algorithm, every loop structure, every textbook definition you can imagine. But when it comes to the exam, Alex overloads their answers with raw computer science facts and provides absolutely no context or critical analysis. It's just a massive fact dump. On the other side, we have Sam. Sam is fast. Honestly, maybe a bit too fast. Sam rushes straight into writing the code the second the timer starts and completely misses the command word requirements. We're talking about missing the crucial difference between words like describe, explain, and evaluate. Both Alex and Sam are working hard, right? But they are both leaving massive amounts of marks on the table. Today, we are going completely under the hood to fix exactly that.
All right, here is our agenda for today's session. Number 1, the pseudocode mark trap. 2, top 3 examiner warnings. 3, the procedural framework. 4, earning method marks. And 5, mastering critical analysis. Let's get moving.
Section 1, the pseudocode mark trap, missing the context.
I want you to treat this explainer as your ultimate examiner's playbook, okay? In Cambridge Computer Science, and this is especially true at the 9618 level, the assessment objectives explicitly target 3 things: your knowledge, your application, and your analysis across unfamiliar contexts. Let me repeat that because it's absolutely crucial. Unfamiliar contexts. If you just memorize a standard bubble sort from your textbook and paste it onto the exam paper, you are guaranteeing failure. There's just no way around it. Examiners deliberately design scenarios you have never seen before to test if you actually understand how the code works. Let's look at this comparison on screen. On the left side, we have Alex. Alex memorized a standard array sorting algorithm using totally generic variables, things like X and Y. But the question actually asked to design an algorithm to monitor temperature sensor arrays in a nuclear reactor. Look at those red pen marks. That is the examiner giving 0 application marks. Why? Because there is absolutely no mention of sensors, no mention of temperatures, and no mention of reactor limits. Alex completely failed to link the pseudocode to the specific context of the question. Now look over at the right side. This is Sam's answer. The specific command word in the prompt was evaluate the efficiency of your algorithm. But Sam rushed in and just wrote more pseudocode. Sam started writing out an alternative search method instead of evaluating the one that was already written. There's no discussion of time complexity. There's no mention of memory usage. Nothing. Failing to decode the command word and failing to link your code to the specific real-world context just destroys your mark potential. You have got to adapt your knowledge to what is right in front of you.
Section 2, top 3 examiner warnings, direct from the reports. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, the principal examiners have spoken, and these right here are the top 3 fatal mistakes candidates make year after year. Let's break them down. Number 1, using the wrong formula or algorithm for the context. Think about it. If the data they give you is already sorted, why on earth are you running a standard linear search? A binary search is exponentially more efficient in that scenario. You must choose the specific tool that fits the context they've given you. Number 2, forgetting to check boundary conditions in edge cases. Guys, this is a huge one in pseudocode. If you write a while loop, ask yourself, does it stop at item 99 or item 100? What happens if the input file they gave you is completely empty? What if a user inputs a negative number when the system is expecting a positive integer? Examiners specifically look for these off-by-one errors and missing validation checks. It's like low-hanging fruit for them to deduct marks. Number 3, providing answers not specific to the given question context. If the exam question is about a library database, your variable names in your pseudocode should be things like book ID or member name. They should not be array1 or string A. Remember, context is king.
So, the real challenge is actually remembering to check all these factors when you're sweating under the high pressure of an exam hall. And here is your ultimate memory hack for that. Whenever you face an algorithm or pseudocode question, I want you to write the letters C, B, S right at the top of your page. C stands for context. Ask yourself, does this algorithm actually fit the real-world scenario they just described? B stands for boundaries. Have I explicitly handled the extreme ends of my loops and my data structures? And S stands for specifics. Are my variable names and my outputs specifically tailored to this exact problem? CBS. I want you to drill this acronym into your mind. Never ever forget the algorithm factors.
Now, when you are asked to document your algorithms, explain your code, or evaluate an approach, how are you supposed to actually structure that answer? Enter the PEEL framework. Point, evidence, explanation, link. This is the absolute ultimate strategy to structure your computer science answers. First, you make your point about the algorithm. Then, you provide evidence directly from your pseudocode. You actually reference a specific line, like writing down as seen in line 4, while index less than 100. Next, you give an explanation of why it works or why it's the most efficient method. And finally, you link it all back to the specific requirements of the question prompt. Let's do a quick mental test right now. Think of a piece of code you wrote recently. What is the main point of that code, and what specific line proves it? If your extended exam answers do not follow this 4-step PEEL structure, I guarantee you are bleeding marks simply due to poor organization.
And that brings us to a major terminology alert. When you read the principal examiner reports, they reveal a consistent, honestly devastating confusion of key computer science terminology. Students are frequently mixing up iteration with recursion, or they confuse arrays with linked lists, or they write compile when they actually mean interpret. Listen, when you are documenting algorithms, your terminology heavily matters. The examiners explicitly state that top-tier candidates define their terms clearly before diving into their extended responses. Don't throw away easy marks before you even start your technical analysis just because you used a loose, unscientific word. Be precise, be professional.
Section 3, the procedural framework. This is the blueprint for success.
All right, this is our transformation phase. We are officially moving away from those messy red ink answers we saw from Alex and Sam earlier. Here is the 5-step standardized procedural sequence. This is what guarantees your programming skills and algorithmic designs are clearly documented and snag every possible mark. Step 1. Identify key elements. Before you even think about writing a single line of pseudocode, list out your inputs, your outputs, and your required data structures. Plan it out. Step 2. Apply relevant principles. This is where you decide if the problem requires a conditional loop, a count-controlled loop, or maybe a specific sorting logic. Step 3. Execute analysis with clear working. This means writing your code logically. Use proper indentation. Show your step-by-step logic clearly. Step 4. Verify results. This is essentially your mental trace table. Walk through your own code with dummy data to catch those boundary errors we talked about earlier. Step 5. Present in appropriate format. Use the standard Cambridge pseudocode conventions. Please, do not invent your own syntax on exam day. If you internalize and follow this sequence, you construct an impenetrable defense against lost marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Earning method marks, showing the process.
So, in computer science, specifically in algorithm design, it is entirely possible to write a final line of code that actually has a slight syntax error, but you still walk away with 80 or 90% of the marks for that question. How is that possible? It's all through the method mark strategy. Listen to this direct quote right from the Cambridge syllabus guidelines. Top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. This proves exactly why showing your methodological process is way more valuable than just writing down a final answer. When you clearly document your variables, when you use descriptive identifiers, and when you map out your logic step by step with comments, for example, explicitly writing / increment sensor count right next to the code count equals count plus 1, you are actively demonstrating that connected, conceptual understanding. You are proving to the examiner without a shadow of a doubt that you know exactly how the algorithm is supposed to work, even if you accidentally drop a parenthesis at the very end, in a rush. Your process is your insurance policy. Show you're working, always.
Section 5. Mastering Critical Analysis. Welcome to the interactive workshop.
Okay, it is time to put everything we've learned today to the test. High-mark questions require you to extract data, spot errors, and evaluate trade-offs under severe time pressure. Here is Challenge 1. Imagine you're in the exam. The clock is ticking, and you have exactly 60 seconds to scan a table that compares binary representation, extracted data, and performance trade-offs. Your data interpretation skills have got to be razor-sharp here. You need to be able to quickly extract the core trend from the binary representations. You need to understand how it translates to denary or hex. And most importantly, you need to instantly recognize the performance trade-offs. For instance, take a look at the image. Notice how the algorithm that uses less memory, the one shown right there in the first row, actually requires significantly more processing cycles. That right there is a classic trade-off. Scanning complex data like this, processing it instantly, and drawing evidence-based conclusions is exactly what elevates you from an average student to the absolute top tier.
Let's move right into Challenge 2. On the left side of your screen, we have a flawed, very generic descriptive paragraph explaining an algorithm. On the right side, we have a high-mark, context-specific Peel paragraph. I want you to look closely at the left side and see if you can spot the fundamental flaw. Look really closely. Did you spot it? The flaw is that it merely translates the pseudocode into English sentences without adding a single drop of a value to value. It literally just says the loop repeats until x is 10. Do you know what the examiner commentary on answers like this says? It's brutal. They write, candidates simply read the code back to the examiner. And guess what? That scores 0 analysis marks. Now look at the right side. It perfectly utilizes the Peel framework. It makes a point about efficiency. It provides evidence by citing the specific loop condition until temperature greater than max limit. It explains exactly why it minimizes memory usage in the specific sensor array scenario. And finally, it links it back to the overarching system requirements. That is exactly how you secure full maximum marks.
And this brings us perfectly to the higher order evaluative thinking that's absolutely required for top marks, which leads into Challenge 3, speed writing. When you are writing your analytical paragraphs, you must be hitting these exact bullet points. First, you need to consider multiple alternative solutions. Don't just say your code is good, explain why it's actually better than the alternative. You must analyze performance trade-offs, meaning you discuss speed versus memory. You need to acknowledge algorithmic limitations. Be honest, where would your code realistically break down? You have to justify your decisions with hard evidence pulled directly from your trace tables. And critically, use comparative connectives. Discuss similarities and differences using words like conversely, whereas, and similarly. Doing this automatically pushes your answer from an average description straight into top-tier critical analysis.
Wow, we've covered a massive amount of ground today. So, to pull it all together, I want to present you with this complete 3-rule answering system cheat sheet. If you internalize and follow this system correctly, you are essentially guaranteeing yourself top marks. Rule 1, command word decoding. Never start writing until you know exactly what the verb in the question, describe, evaluate, explain, is actually demanding from you. Rule 2, Peel framework application. Structure every single extended answer with point, evidence, explanation, and link. Rule 3, time management matrix. Allocate your exam time strictly based on the marks available, ensuring you always leave time to check those CBC boundary conditions and edge cases we talked about. Honestly, screenshot this slide right now. Memorize it. Live by it.
You know, the students who actively implement these exact computer science strategies, the ones who shift from rote, robotic memorization to systematic procedural frameworks, they see an average improvement of exactly 2 grade boundaries, 2 full grades. That is literally the difference between sitting at a C and jumping to an A. But here's the catch. They only achieve that if they practice consistently and apply these techniques under real, timed exam conditions. This isn't just theory we're talking about. It is proven social proof. You have the tools in your hands right now. It's time to put in the actual work.
Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Now, I want to hear directly from you. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here. Ask yourself this before you go. When you look at your next algorithm, are you just writing lines of code or are you actually engineering a solution? Stay focused, trust the process, and I'll catch you in the next explainer.